Welcome everybody to the dissertation of Moataz. He's going to be talking about using market-based incentives to help with smart grid regulation. So Moataz has put in a lot of hard work into his dissertation. I was about to say I feel for these students having so many crazy things happening in the world and working from home and trying to write your dissertation in the middle of all that too. I think I'm having a hard enough time focusing on my own work. So I really am grateful that Moataz was able to get this all pulled together in the midst of several overlapping crises. But Moataz has done really good work. I'm quite proud of what he's accomplished. And the way this will go is we will have Moataz present. I believe Moataz is targeting about 40 minutes of presentation.
Yes.
Then we will take questions from the general audience. After that, we'll ask everyone in the general audience to leave. Anyone who's not either Moataz himself or on the committee will leave. And the committee will ask Moataz their questions. So Moataz, so I would urge the audience to, if you have like minor like clarification questions, or if you want to see a graph or an equation for a little longer, go ahead and interject during the presentation. If you have a question that you feel is going to take more in-depth discussion, then I would save that for the end. Moataz, does that sound fair to you?
Yes, perfect.
Okay, great. Well, the floor is yours, Moataz. Take it away.
Okay. All right. So thank you, everyone, for being here today. Really appreciate it. So let's get started. So the title of this dissertation is Using Market-Based Incentives as a Control Mechanism to Leverage Distributed Storage for Electric Grid Regulation through the Demand Side. So why are we interested in the demand side, and why are we interested in regulating the electric grid, and what do we mean actually by regulating the electric grid? So this takes us to start with some background. So for the demand side, we're mainly concerned with buildings or residential buildings. And if you can see in on this pie chart on the left, there's the energy consumption in the US by sector. You can see that the building operations consumes around almost 42% of the total energy consumption in the US. This is for the energy consumption. If you look at the right pie chart, you can see that the building operations are consuming almost 75% of the electricity consumption. That's a big amount. So that's why we're interested in kind of regulating this and try to get benefits from the demand side to help to be able to regulate the operation of the grid. The second thing is there is something called the dot curve. This dot curve was introduced in 2013 by this CAISO, which is California Independent System Operator. It's a non-profit system operator serving California. They introduced this curve back in 2013. So this is a 24-hour period. Here on the y-axis, you have megawatts, which is electricity energy net demand, actually. You have here different levels of solar penetration. And when you go like to the highest level of solar penetration, you will find that you will need a ramping almost around 13,000 megawatts in a matter of 3 hours. That's a huge amount that will be needed in this short time. So it's a problem that actually grabs the attention of a lot of researchers. That's why we are interested into looking into this problem. So the objectives of this dissertation, actually, so for the committee members in the dissertation document that I sent out, I initially wrote down 5 objectives. I combined now the last 2 objectives, objective 4 and 5, into 1 objective. So we have a total of 4 now. So just a small change in chapter 1. There is nothing else changes. So our first objective is to investigate potential cost savings in operating residential houses, air conditioning systems, and electrical energy storage systems. And for this objective, we have published 2 papers. There's one in the Proceedings of the American Control Conference. The other one is in Computer-Aided Chemical Engineering Journal. And then for the second objective, which is investigating the use of distributed solar photovoltaic with battery storage systems in a proactive home energy management system. And of course, we will get to the details of this. We also published a paper for this in the Electricity Journal. And then the third objective is using variable electricity prices to leverage distributed storage and flexible loads, a smart grid environment utilizing machine learning techniques. And for this objective also, we have published a paper in Processes Journal. And then the last objective, which is the most interesting one, we'll get to that. We're utilizing a game theory approach, a non-cooperative game theory approach with dynamic pricing profiles to solve the dot curve at different levels of solar penetration and different battery specifications. And for this one, we have an accepted paper in energy conversion and management. So just before getting started, I want to highlight some of the original contributions of this dissertation. The first thing is that we developed a dynamic yield time optimization model that utilizes linear programming to minimize the electricity cost for the end users using first principle models. So the first principle model that we'll be using is just simple heat transfer equations, and you will see we're not using any complicated first principle models, but the problem itself will get complicated when we add different levels of optimization to it. And then using the developed non-cooperative Stackelberg game, and we'll get to that and define what is this, we'll be able to optimize the operation of the smart city model by flattening the net electricity demand curve. And then the third point is that we're going to study some techno-economic feasibility. We'll do a techno-economic feasibility analysis for the smart grid model at different levels of solar penetration with different battery specifications for both the demand side and the supply side. And then before getting started, also I have some definitions that I'll be using through the presentation, some of the metrics that we'll be using so that we don't get busy with defining them later. The first thing is we have the levelized cost of energy. It's basically the annual capital cost plus the annual operating cost divided by the energy generation annually. And then we have an equivalent term called levelized cost of storage, which is, this one is for batteries. The other one is for like if you have a power plant. So this one is for batteries. So it's the battery annual capital cost plus the battery annual operating cost plus the battery annual charging cost, because you're charging the battery with some money as well. And then it's divided by the amount of energy discharged from the battery. And then there is a simple payback period. And I have two definitions here for the simple payback period, one for the PV plant and one for the energy management system within each house. So for the PV plant, this is the total investment cost divided by the net cash flow. And the net cash flow is basically the money coming in minus the money going out. The definition is different for the energy management system in the houses because there is no income actually. There is actually cost savings. Moving from one case to another, from a non-optimized case to an optimized case, you'll be doing some savings. So the definition of the payback period here is the total investment cost divided by the annual cost saving. And then there are some other metrics, statistical metrics that we'll be using to compare the machine learning technique. We have the coefficient of determination. It's calculated using this equation. So we have this Y actual and Y model. So Y is basically the electricity demand. And by the actual, I mean here as a result that I'm getting from my Simulink model. And by the model, I mean the machine learning technique. And then we have the root mean squared error, and we have the normalized root mean squared error, which is basically the root mean squared error divided by the range of the actual demand. And then, so before starting with the first objective, I want to highlight that we're using here, in the whole dissertation, we're using a simulation-based approach. And basically, each objective we're building, each objective is built on one is built on the other one. So I thought that maybe we could start with this and highlight how this has evolved through time. So first, we started with a smart home energy model with battery storage, and we did the dynamic yield time optimization for this. And this will be presented in objective 1. And then we added rooftop photovoltaic to the system, and then we started the economics of this system. This will be in objective 2. And then we made a community of smart houses, and we did the electricity demand prediction models, and this will be in objective 3. And then last thing, in objective 4, we have this grid model, smart grid model, and we perform a pi-level programming optimization of this using the game approach. And then we did an economic study for all parts of the system. Let's get started with the first objective. The first objective, we want to investigate how could we save costs in residential houses just through the HVAC or air conditioning and electrical energy storage. So the hypothesis here is that if we use variable electricity prices with a good energy management system, we would be able to reduce the electricity cost and shift the peak demand. So we're going here to compare two different pricing structures, time fuse and real-time pricing, and I will introduce them in the next slide. But let's look at this figure here. So we have our house here. This house has some indoor temperature, those two. So let's go this direction first. You go with the indoor temperature, it goes to a linear programming solver. This linear programming solver will give you the temperature set point for the next hour. You will take this and go to a temperature controller, basically a PI controller. And then using the indoor temperature and the new set point, it will determine the amount of cooling energy needed to reach the set point. And then also the linear programming solver will give out the battery and charge and discharge energy. So if the battery is charging, you'll be getting energy from the grid to the battery. And if it's discharging, you're either using this energy in the house or selling it to the grid. So let's start with the heat transfer model for this house. So we have here the rate of a change of the indoor temperature is basically this equation. You have this A term, it accounts for all the thermal masses of the houses, like the heat capacities and this stuff. And then we have this B term here that accounts for the overall heat transfer coefficient and the surface area of the boundaries. And then this delta T here. So we have this T amp here. So what is the ambient temperature here? So I'm using TMY3 data or typical meteorological year data for Salt Lake City, Utah. This is basically what I've been using. I'll be using through the whole dissertation. And here T house is basically the indoor temperature or the temperature set point. And then we have this Q here. This is the cooling power. Remember that this equation here is a differential equation, so it's per unit time. So this is power, not energy. And then we have a fitting parameter or this constant term, which accounts for all the neglected, any source that we neglected, mainly something like ground temperature or radiative heat transfer, because we're only using this equation. There's no radiative heat transfer here. So I use this term just to account for those neglected stuff. So this was for the heat transfer model. What about the battery model? The battery model is very simple. We have the rate of change of the state of charge is defined as it's the efficiency of charging multiplied by the charging power minus the efficiency of discharging divided by the discharging efficiency. So those equations actually, they will be in all the next objectives. I'm just explaining them here, and I will not get back to them later. And then the linear programming model, we'll also explain this once because this is also going to be with us in all the objectives. So we have here the objective function is that we want to minimize the electricity price. So here PI is the electricity price, unit price actually, in dollars per kilowatt hours, multiplied by the cooling electricity consumption. Remember that before it was the cooling power, yeah. So this is calculated from this equation. So the other one was Q dot, this one is Q only, so this energy divided by the C rating would give you the cooling electricity consumption. So what is the C rating? This is something called the seasonal energy efficiency ratio. It's a property of each air conditioning system. So this dissertation as well, for each house, I have a specific value for each air conditioning system in each house. And then we have two equality constraints, which is the two equations that we have seen before, the battery and the heat transfer equation. And I'm not showing them here, but I can elaborate on this later. And the decision variables here are the temperature set point, the battery charging and discharging energy. And for the committee members, I believe maybe in the dissertation, I wrote actually here that I'm minimizing, and I wrote here the cost actually, arrange for the cost. So this is wrong actually. This is the correct one. I will correct that because the cost here is not the decision variables. The decision variables are the temperature set point, the battery charging, and discharging energy. So we're using time fuse profile and real-time pricing profile. The time fuse profile, this one exists in Utah. It has just two different values through the day, and the average value is 11 cents per kilowatt hours, and this is actually the average value in Utah. And this real-time pricing profile, this is a customized profile that would help us in shifting the peak demands to off-peak hours. And also the average over 24 hours is also 11 cents per kilowatt hour. So let's take a look at some of the results here. I'm showing the legend here because I know that you can actually read the legend here. So actually you can get lost if you go through everything here. So the first two figures here is one both for time of use, one without battery and one with battery. And this two is for real-time pricing without battery and with battery as well. So I want you to focus on this electricity curve, on the black curve. So you can see here that without battery in time of use, we had a big demand at almost 5 p.m. And then when we use the battery, this peak demand was shifted to almost between 11 a.m. and 12 p.m. So time of use was able to shift this peak demand. What about real-time pricing? So real-time pricing, you have the peak demand actually in the morning, because remember that the prices are higher here and low here. So when the prices are low, you're consuming the maximum amount of energy that you can consume. And then, so when we use the battery, we actually didn't shift the peak demand, but it reduced it, because you're using the battery here. At some point, you're charging the battery and then discharging it, then it's charging it again. So the battery was helpful in just shaving this peak. And then if we look at some of the economic results here, you can see that the time of use without a battery and with battery have energy costs less than the real-time pricing without battery and with battery. Also, the energy usage as well is much less here in time of use than real-time pricing. Also, the savings is higher in case of time of use. This is an interesting result. You would think that if you change the price every hour, that would be beneficial and you would make more savings. But actually, this is not the case. So we found that time of use pricing structure was able to shift the peak demand, and it was able to reduce the cost and reduce the energy usage. So this means that you don't have to change the price every hour. You can actually change it every 4 or 5 hours. And this is actually the basis that I will be building on actually in Objective 4. So this was for Objective 1. So we had 2 publications for this again. And then we'll go now for Objective 2. Objective 2, we are now using distributed solar PV with the battery storage system, with also a proactive home energy management system. So the hypothesis here is that if you use rooftop PV with battery storage and a proactive energy management system, this system will be economically feasible. So actually in the literature, a lot of people are saying this is not going to be economically feasible because the electrical energy storage or the batteries are very expensive. So we will look into that. So we're comparing slab pricing with real-time pricing. So slab pricing is basically when you have just one constant price through the day. So, and we will look into the levelized cost of energy and the simple payback period. So how does the system work? So let's look at this one first. This figure is a case without a battery. So we just have the rooftop PV, which is here, the solar production, this blue curve. It increases in the morning times, and then in the afternoon times it goes down. And then you have this demand, this orange curve. It's basically the energy consumption by the house. This is just a schematic. It's not a real value. I'm just illustrating how does the system work. So the net grid consumption will be that here you'll be exactly the same as the demand. And when the solar starts to appear, this net demand will go down, and then it will go up again when the solar disappears. What happens when we use a battery? So this is like the perfect case when you use a battery. So when you use a battery, you will actually start charging your battery here when there is excess solar production. You'll be charging your battery, and then when the solar goes down, you'll be using this battery to supply energy for the system. And then when the battery gets empty, you will go back to this demand here. So this is just an illustration of how does the system work. And here we are looking at 10 different cases. We have 4 cases with slab pricing and 60 cases with real-time pricing. I actually want you to focus mainly on case number 7. So what is this case? So we have here two different billing structures, net metering and no payback. So net metering means that if you're buying electricity, let's say it was 11 cents, you'll be selling it with 11 cents as well. You'll be selling your excess production with 11 cents. No payback means that you'll not get paid for your excess production. So I am interested in this case. So this case is with real-time pricing, net metering. We have PV plus battery and optimization. So it has everything all together. So if we move forward and take a look at those curves, so for case 2 and 4, actually, if we go back here, case 2 and 4 are basically the same cases. It's just the economics part of it is a different thing. So case 2 and 4, you're just charging the battery when solar appears, and then you discharge at night. So we're using here some heuristic approach for the battery to charge and discharge the battery. There is no optimization. The optimization only appears in case 7 and case 10. But case 10, there's no payback. That's why it's worse than case 7. And then for case 6 and 9, you can see that we're also charging when the solar appears. But then for case 7, because this is an optimized case, it doesn't necessarily charge when there is excess solar production. It actually charges when the price is the lowest. So it charges here, and then it charges here. And then for case 10, also didn't start charging from like when solar started to appear. It actually started later on. So the optimized cases doesn't actually charge when there is excess production. It charges when the price is lower. So let's take a look at those results here. So again, focus on case number 7. So this is the annual electricity consumption. You can see that actually case number 7 is consuming more electricity than all the other cases. But on the other side, the annual electricity bill, case number 7 is actually in the negative territory here. So the homeowner is actually making money out of this case. So, which is by using the energy management system and the rooftop PV and electrical energy storage. Also, if you look at the payback period, only case 7 is the case that's lower than the system lifetime. The lifetime here is the PV lifetime. And we're assuming that it's 25 years. And if you look at the levelized cost of energy as well, in case 7, it's 0.07, but in all the other cases, it's like 0.19, 0.3, 0.22. So it's significantly lower than all the other cases. So this concludes that case 7, which is optimized case with PV and battery under net metering billing scenario, this shows that if you use the right utility rates and energy management system, this investment process could be possible. Like it can be, you can actually make profit out of this. And then, so this was for objective number 2, and we have an application for this in the safety journal. And then let's move to objective number 3. So in objective number 3, we want to use variable electricity prices to leverage distributed storage and flexible loads, which is basically the air conditioning system, utilizing machine learning techniques. So the hypothesis here is that when you manipulate the electricity prices through these prediction models, you will leverage the storage and the flexible loads to regulate the grid. So we'll be comparing different machine learning techniques, and the methods that we will be using are R-squared, root mean squared error, and normalized root mean squared error. And this is the grid model that we have here. We have a community of houses, 60,000 houses, and we have a solar PV plant. And then this is the primary source of energy, and the thermal power plant is the secondary supply. So when solar is not available, you'll get your supply from the thermal power plant. So we did the machine learning techniques that we use is we use Lark's regression, which is linear autoregressive regression model, and nonlinear autoregressive regression model, and nonlinear autoregressive neural network model. And we did 2 prediction mechanisms. So there's one step mechanism and 2 step mechanisms. So what does this mean? So the one step mechanism you have here, R here stands for the electricity price. So you go with the electricity price and the ambient temperature, you go through the model, and it gives you directly the energy demand. But in the 2-step mechanism, you go with the energy price and the ambient temperature, you go through model 1, it gives you the state of charge of the battery. So this is an intermediate step here. You're getting how is the battery performing. You use this with electricity price again and the ambient temperature, go through a second model, which gives you out the demand. So we will look only into the results of the neural network model because it's actually the best one. And I will focus only on the one-step mechanism because we found that the results for the one-step mechanism and two-step mechanism are actually comparable. So the two-step mechanism is slightly better, but the one-step mechanism will be preferred because it will be faster. You only have one model, and it can be used easier than the two-step mechanism. So the NarcSnet was the one-step mechanism. This is the preferred model, and it's got the R-square value of 0.6p. You might think that this is a small value, but actually there are a lot of sources of errors in this system. So we're not, for example, we're not accounting in this model for the lighting of the house. We're not accounting for anything rather than the air conditioning systems and the battery storage. So there are other sources of energy consumption, and we're not considering that. So actually getting an R square of 0.63 is not that bad. And we have a root mean squared error of 89. So how can you understand what does this number mean? So if you look here at this parity plot, you can see that the range of the data is going up to something like 600. So if you have your error is something close to 90, it's not actually that bad. And then you have the normalized root mean squared error. You can think of that as a percentage. It's like 10% error. It's also not that bad. Taking into account that there are a lot of errors in this model anyway. And here's the validation of the model against actual data. And again, the actual data, I mean here the data from the Simulink model. So this would be the data from the Simulink model versus the data from the NarcSnet. You can see also that they are matching in a good way in this figure. So this is actually 24-hour period. If you look into a bigger horizon, maybe there will be some other days that doesn't fit perfectly like this one. So this means that we were planning actually to move forward using the NarcSnet model to solve our problem that we will introduce in objective number 4. But we found that it will be better actually if we use the Simulink model itself, because the Simulink model itself doesn't have all the errors that we have here in this neural network model, and we actually want to focus on proving the concepts that we have rather than just applying different machine learning techniques. So we moved forward without those prediction models. We actually use the Simulink model directly, and this will actually lead to some interesting concepts that we will introduce next. So this was for objective number 3, and we published the paper here in Processes Journal. And then we go to objective 4, which is the last objective. So objective 4, which is this kind of an interesting study here. We're utilizing an uncooperative game theory approach and dynamic pricing profile to solve the duck curve at different levels of solar penetration and different battery specifications. So our hypothesis is that if we use dynamic pricing profile with a robust grid optimization scheme, we will be able to flatten the curve. And we will be able to flatten the duck curve, not the COVID-19 curve. So if you look here at this figure, this is just also a schematic to illustrate how would we be able to solve this system. So if you can see this curve here, the one without energy storage. So if you look here, this is the area under the curve. The one that goes up is the one without energy storage. So you can see that there is huge ramping happening in a matter of like 5 or 6 hours. It goes actually from below 0 to a value of almost 80 megawatts. And when we use the energy storage, also with HVAC, you will find that this curve is shifted upward a little bit, and this one is shifted downward a little bit because you are charging here, and this is charging here. So that the curve would get a little bit more flat. So this basically is the concept that we are trying to introduce here. So we'll be comparing different smart home automation cases at different PV plant sizes and different battery specifications. So we'll look at the levelized cost of energy, levelized cost of storage, and the payback period. So let's talk about this game theory approach. So we're doing here something called non-cooperative Stackelberg game. So this approach was introduced by a German economist His name is Heinrich Freiherr von Stackelberg. So in German, it's Stackelberg, not Stackelberg. But anyway, it doesn't matter. So what does this game mean? So this game is actually a strategic move between a leader and some followers. The leader will be doing some optimization, and the followers will be doing another optimization. And they are kind of chasing each other or working against each other. So a good example for this is actually our system. So our system here, we have this smart grid model. We have an upper level optimization or a grid level optimization. We're trying to flatten the dot curve in this upper level optimization. And then we have a lower level optimization only for the houses, which is trying to minimize the cost for the end users. So how does this optimization problems look like? So the leader optimization or the upper level optimization has this objective function. So we're trying to minimize, remember that we're trying to flatten the dot curve. So how can we do this numerically? So you're trying to minimize the standard deviation of the net electricity demand and the standard deviation of the electricity prices. And here the alpha here is a weighting factor, because remember that the prices are in the order of magnitude of, like, the price can be like $0.1 per kilowatt, something like that. But the energy demand can go to like 100 or something. So we have to use a weighting factor so that both terms can be considered in this optimization problem. So I did some tuning on this weighting factor, and I found that a value of 20 worked good for the purpose that I need. And then the range for the prices here, so the prices here are the decision variables. We're going actually from a negative value, means that you're paying the end users to use electricity, to a value of 0.23. So why am I using a negative value? Because in some cases you would actually have some excess generation or something, and you want to get rid of that. You would give money to the end users to use that. And then the standard deviation is basically the basic standard deviation equation. So remember that for the net electricity demand, we have 24 data points, but for the electricity prices, we have 48, because this problem is being solved for 24-hour period at every hour. So in the last hour of the day, you'll be solving, you would need the next 24 hours prices to solve the problem. So you would end up having 48 prices, not 24, because this problem is being solved also on a receding horizon, where you actually solve the problem for 24 hours, but you use the first hour only, and then you move to the next hour, and you solve it again for the next 24 hours. So, and this is the objective function is solved using particle swarm optimization. So why am I using meta-heuristic algorithm here? Because this equation, or this optimization problem, is actually nonlinear and non-convex. So using a meta-heuristic algorithm will help us to address the uncertainties with this system, and it's to be more efficient than any other optimization technique. So this was for the leader optimization. The follower optimization, remember that we talked in objective 1 about the linear programming model. This is actually the followers optimization. So I'm not showing this here. So let's take a look at this figure. I'll actually give just some high-level overview. I won't go into details of this. So what I want to highlight here only is that we have two sides. You have, on the left-hand side, you have the leader optimization. On the right-hand side, you have the followers optimization. The problem first initial guess for the electricity prices. You send this information to the followers. Problem gets solved. You get the net electricity demand. You send this information back to the leader. The PSO works and evaluates the objective function, and then you exit when you hit the exit condition. So it's just a high-level overview of this figure. And then let's look at the different cases that we're looking at in the smart home automation system. So we're looking at flat pricing and dynamic pricing, and we're looking at three different cases: a case with HVAC optimization only, a case with battery optimization only, and a case with both HVAC and battery optimization. And I will show the results only for the cases of HVAC and battery optimization, because they're obviously the best results. So if you look here at this figure, so I am showing 1 day per month. So every month I'm showing 24-hour values. So here you have on the y-axis, the left y-axis is the net electricity demand, the right y-axis is the electricity price, and then the time is just 24 hours in each figure. So the blue curve is the case without optimization or the case with flat pricing. The red one is the optimized case, and the black one is the dynamic pricing profile corresponding to the optimized case. So if you can look at the summer months, mainly August, I like this one a lot. You can see that the curve actually in the optimized case is almost horizontal, actually. It's getting flat here. So if you compare it to the other months, this one is actually the best one. Also, September is also very good, July as well. So you can see that the general trend here is that in the summer months is better than the other seasons. Especially in winter, the performance is not that good, but it's actually still better than the cases of HVAC only or the cases of battery only. That's why we're looking into this case. So these results were actually for a system that has 100 megawatt PV band and this battery capacity. So it's 597 megawatt hours. So why is it not 600? Why is it 597? Because I'm actually using here real battery designs from Tesla, the company. We have battery designs called Tesla Powerwall, and we have two different designs. We have one that's 6.4 kilowatt hours, and the other one is 13.5 kilowatt hours. And my system has 60,000 houses, so I assume 30,000 are using the 6.4, and the other 30,000 are using the 13.5. If you get the summation of that, you'll find it 597 megawatt hours, 597. That's why it's not 600. So let's look at the economic study cases here. So there are a lot of cases. We have 20 cases. There are 4 of them we're trying to figure out with the same battery design, what happens if we change the charging and discharging rate. So those are different charging and discharging rates. And then the rest of the cases from case 5 to case 20, we're using different PV plant sizes because remember in the results that we've seen before, it was a fixed PV plant size, 100 megawatts. Now we're looking at different sizes and different battery capacity. So for the first 4 cases where we are looking into the charging and discharging rates of the battery, you can see that as the charging rates increase, you will see that we have here the total installed cost and the annual income for the PV plant. We have the total installed cost for the energy management system, and we have here the total installed cost for the PV plant. You can see that the total installed cost for the PV plant is 130 million, but the values here for the energy management system is much higher. So this means that you know that the batteries are more expensive for sure. But if you look at case number 1, actually is not very good because 1 kilowatt you're charging the battery at a rate of 1 kilowatt, and it's the battery is 13.5 kilowatt hours. So you will take 13.5 hours to charge the battery. That's a long time. But if you look at the 2 kilowatts, this will take something between 6 and 7 hours. This is a better case. So actually, if you look at those results here, the payback period is a determining factor here actually, because in case 4, you see that the payback period here is 50. That's over the system lifetime of 25 years. And so actually the recommended cases are case 2 and case 3 in this case. And then from case 5 to case 20, so of course you don't have to remember what each case is. You just have to remember that as the number increases going up to 20, the size of the system increased, like the PV plant size increased and the battery capacity increased. So the general trend here is that the levelized cost of energy for the PV plant is very small compared to the levelized cost of storage for almost all the cases. And in some cases, it goes up to something close to 0.6 value here, but the levelized cost of energy is actually less than 0.1, it's 0.07. So very small compared to the other results. Look at the payback period. Some cases go over the system lifetime of 25 years. So this actually, those cases are not feasible, but some other cases are below this 25 years value. So look at case 20 here. This case has the biggest PV plant size and biggest battery capacity. And there are some other cases as well that are below the 25. But I'm interested in this case this case, so this means that this very big system is actually economically feasible. So that should be recommended. So we should look into this figure. This is figure for case 20. To find that actually with this big battery capacity, you're charging the battery like that, and then you're discharging here. So you actually didn't solve the problem. So the problem was actually going from almost -50 up to 100. You're now going from 200 to -150 or -200. So actually, this case is not feasible. This made me think that maybe we need to modify our objective function or to account for higher levels of solar penetration and maybe solve the economic problems that we have seen before. So I modified the leader optimization. I changed the range of the decision variable. There is no negative now. I'm using positive values, and I reduced this one from 0.23 to 0.2. So why did I do that? So actually, for the 0.2, we'll get back to this, and I'll tell you why. But I'm just seeing that with the negative prices, it didn't actually help that much with the economics of the system. So I just decided to use positive values and see what's going to happen. And then I added another term here, which is actually the revenue of the solar PV plant. So remember that in the lower level optimization, we're minimizing the cost for the demand side, but we didn't say anything about the supply side. So we had to introduce this here. That would be accounting for the economics of both sides. Remember that there is a negative here, and this is a minimization. It means that we're maximizing the revenue for the supply side. So we're looking into different cases here rather than the other ones. We have 10 different cases. We're increasing the level of solar penetration. There is 400 megawatts now. Before it was 200 only. And we have two different cases with two different battery capacities. I use 5971, and then this value is just this value divided by 2. So the Tesla Powerwall designs and just 1/2 of those designs. So the results here, I'm looking only for the results for case 8. Actually, the best results are for case 8 and case 9. And I will tell you why. So for case 8, if you can look here, I'm showing the results for 3 months only. I'm assuming that January is accounting for the winter season, August for the summer season, and May is representative for the for spring and fall. So you can see that the curve is getting flat, and actually getting flat close to 0 in this case 8, which is 200 megawatt PV plant and this battery capacity. The curve is getting flat around 0 in May and in August as well. But in January, it's shifted upward a little bit because in January there is a lot of heating happening. That's why the curve shifts up. And then if you look here, those bottom figures, this is the state of charge of the battery. So the battery is getting charged here through the day, and then it gets discharged but doesn't go down to 0, because if you discharge the battery down to 0, it means that this curve would go down like this. So it wouldn't be flat. So remember that our objective function is accounting for the standard deviation of this curve. That's why the battery is not getting discharged down to 0. If the objective function was purely about the economics only, of course this one would go down to 0. So, and it's actually charging up to the maximum capacity, which is close to 600. Remember this number. So this case 8 and case 9 as well, I'm not showing case 9 here, are the best two cases. Case 9 as well is comparable to case 8. If we look at the economics, you'll find that numbers drastically changed over the previous one. You can see that, remember that there was a lot of cases for the levelized cost of storage that are going up close to 0.6. Now we only have one case going there, and there's most of the other cases are getting close to the levelized cost of energy for the PV plant. And if you look at the payback period, actually all the cases are less than the 25-year system lifetime. So how did this happen, or why did this happen? Remember that we changed the range of the prices. We were using only positive values, and we reduced the upper limit. So if we go back here, actually do that. If you look in, for example, in February here, in some of the cases, the optimizer will try to stick to the upper limit of the prices. So it's here at 0.23. So if we lower this upper limit you will actually save some cost. So remember, you might say think this is not significant, this is just 0.03, but remember that 0.03, this is just for 24 hours, just for one house. Think about the whole lifetime of 25 years and a community of 6,000 houses. The savings will be very big. So that's why case number 8 and 9, remember that they are getting flat almost around 0. So why didn't consider case number 10? Because it's actually case number 10, you have higher solar penetration. So the curve is getting flat, but it's down. It's actually not getting that flat, and it's going down to far in the negative zone, which is something nobody prefers. We want to be close to 0 or above 0. So this means that we conclude here that case 8 and case 9 was 200 megawatt PV plant and 300 megawatt PV plant are the most promising cases. And they have a potential of having solar penetration levels over 50%. Actually, it's approaching 100% because the curve is getting flat around 0. But we cannot say it's 100%. It's just something over 50% because we're not sure whether this accounts for all the system or not. Like, I don't know whether we can make it flat around 0 or not to say that we have 100% solar penetration. It's not 100%. It's something over 50%. So that was the last thing for this objective as well. So just a reminder with the accomplishments here. We have the first 2 publications are for the first objective. This one is in the Proceedings of American Control Conference. This one is Computer-Aided Chemical Engineering. This one is Prestige Journal. This is for Objective 2. And then for Objective 3, we have this Prestige Journal publication. And then we have Energy Conversion and Management for Objective 4. And I have another paper that I'm a second author on. And I did some 3 conference presentations. One is the American Control Conference in Milwaukee, Wisconsin. And the other one is called Process Systems Engineering Conference. This one is in San Diego, California. The third one was called the Energy Policy Research Conference. This was in Boise, Idaho. So the conclusions of this dissertation is that we've used a simulation-based approach and we designed a novel citywide dynamic model. This dynamic model would utilize dynamic pricing profiles to leverage distributed storage and flexible loads. And we have seen that we were able to flatten the curve around the value of 0. So our suggestion from this dissertation is that the demand side shall play a significant role in future for stabilizing the power grid and flattening the duck curve. And the last thing is that this should encourage policymakers to utilize those dynamic pricing profiles to incentivize the end users to invest in electric storage and smart home automation systems so that they can be an asset to the grid and help in regulating the operation of the grid. So the last thing that I have here is just some acknowledgements. I would like to thank my advisor, Dr. Kody Powell, for his guidance and support over the last 4 years. He's been very helpful and very supportive to me. So thank you, Kody. I would like to thank my supervisory committee for their comments and for their feedback. So thanks everyone. I would like to thank all the members of our research group. And here I would like to acknowledge Dr. Kazra Mohammadi because he helped me a lot with my last paper. So thank you, Kazra. And I would like to thank the Department of Energy for their financial support over the last 4 years to the Industrial Assessment Center. And for this one, I would like to acknowledge Julie Sieving, the co-director of the Industrial Assessment Center at the University of Utah, for her mentorship and her guidance while we were working on those industrial assessments. So thank you, Julie, for this. Last thing, just I would like to thank my family and my friends for all the love and support over the last 4 years. And thanks to everyone who were online here today. I really appreciate it. And so thank you. That was the last thing that I have.
All right, thanks, Moataz. Feel free to join me in giving Moataz a big hand.